Hello and welcome back to lecture 3. As you can see, today's topic is matrix transformation, and this is the first part of the topic. In this part, we are going to talk about how on earth can a matrix possibly describe a linear transformation, what is their relationship, and so on, stuff like that. So let's begin. Well, we have been talking about linear transformations for a while now, and we have one right on our screen right now. This is a transformation from the set of r squared to r squared, so which means we are dealing with two-dimensional vectors. We have an example, 3, 2 vector right here. This is another notation of writing a vector. X is the first component and y is the second component. So what the transformation is defining here is that any vector you pass through it, it is going to multiply the first component by a factor of 2 and multiply the second component with -1. So if I pass the vector 3, 2 through the transformation, I will end up with 6 and -2. Now in our last video, we raised a question, and that question was, this is exactly like a function, so why aren't we using the word function and just invented the new word transformation for the same purpose? Well, to answer that question, let's first look at the visual representation to have a better understanding. So this is our vector. If I apply the transformation to it, I'll get another vector, and that is the yellow one right here. Now this looks like a function, but we prefer using the word transformation because the word transformation refers to some sort of movement, and the way we like to think about transformation is that this vector, when I apply the transformation to it, moves from this original position to a new position, and as there is some movement or motion involved, transformation is the more appropriate word. Now, the interesting fact about this, and what actually is the topic of this video, is that we could have expressed this same movement or the same transformation using a matrix multiplication. If you recall our matrix lecture, we showed an example of this. When I multiply a matrix to a vector, we get a new vector. In this case, we are getting the exact same vector that the transformation gave us. And this is not only true for this one vector. If you take a bunch of other vectors and multiply the same matrix to all of it, you get the transformed vector for each and every one of them. And if you recall, this xy plane that you are looking at right now is actually r square, a collection of infinite vectors. So every single point on this xy plane denotes a vector. For example, this point here and this point here are these two vectors. So what happens if I multiply this matrix right here, the 2001 matrix, to each and every single point on this plane? The matrix is going to shift the whole space into something new, and that movement can be seen like this. As simple as a matrix looks, it actually possesses the power to transform, to squish or morph space itself. So what we can learn from here is that every matrix performs a transformation. If we have an n-dimensional vector, and if we multiply it with a matrix of m into n dimension, the column of the matrix has to be n, otherwise the multiplication wouldn't be possible. So if I multiply this matrix with an m into n dimensional matrix, the result is going to be m into 1 dimensional vector. So this transformation that is taking place here is a transformation from Rn to Rm, because our input vector is n dimensional and our output vectors are going to be m dimensional. For now, we are working with only square matrices. That means we are working with n into n matrices, so our input and output vectors are going to have the same dimension. Now let's look at a few more examples of how a matrix can transform a space. In our first example, we are multiplying every vector in this xy plane with the identity matrix, and as you can see, the space did not change at all, and that's because multiplying a vector with the identity matrix results in the same vector. So the transformation is t of x equal to x, nothing changes. In our next example, we have a 45-degree rotation, and this is the matrix for that. If you multiply any two-dimensional vector with this matrix, you will get another vector which has the same length but has a direction that is 45-degree counterclockwise shifted to the original vector. Our next example is a scaling transformation. everything along the y-axis remains the same, but everything along the x-axis or the horizontal axis has been scaled by a factor of 2. So our house looks very wide here, and this is the matrix to do that job. The next example does a rotation again, and this is a 255-degree counterclockwise rotation, and this matrix will do that job for you. A matrix transformation can even change the angle between the two axes, so the x-axis and the y-axis does not have to remain perpendicular all the time. In the next example, we have one such case. In this example, our y-axis have shifted towards the right while the x-axis remains in place. This is called a skew or a shear. As the skew has occurred parallel to the x-axis, we call it a horizontal skew. So we can see that a matrix causes some transformation, but we are avoiding an important question. Because every transformation is not linear, how can we be sure that these transformations that the matrices are causing is always going to be linear? Well, it is actually quite easy to prove. Let's say we have a transformation T. If T is a matrix transformation, that means T of V is going to be multiplying V with some matrix. We also know that each and every linear transformation is going to satisfy this condition. Now let's see if our matrix transformation follows this rule. We start from the left-hand side of this equation. So we are transforming some linear combination of the vectors u and v. As the transformation is defined by a matrix multiplication, we can write it like this. We know that matrix operations are distributive, so this expression can be written in this manner, and as c and d are both scalars, they can be taken out of the multiplication towards the right, and we have a dot u, which is just the transformation of u, and a dot v is just the transformation of v according to our definition. So we have proved very easily that every matrix transformation follows this statement, and that is why every matrix transformation is a linear transformation. But you have to remember that the opposite is not always true. Every linear transformation is not a matrix transformation or cannot be expressed by a matrix transformation. For example, our apple and juice example was not a matrix transformation because that transformation did not involve real numbers. Also, linear transformations can occur between infinite sets, and as we know, matrices have to be finite, so matrix transformation cannot describe infinite linear transformations. But you don't have to worry about any of that, because in this course we are only working with finite elements that are made with real numbers, and for those elements a matrix transformation and a linear transformation means the same thing. Now let's look at another important aspect of matrix transformation. If I multiply a vector with a matrix, I get another vector as output, which is shown by this movement in this picture. But what if from this position I want to get back to my original position? How should I achieve that? And that answer is the inverse of a matrix. If I multiply this transform vector with the inverse of our original matrix, that will just take me back to my original place. And that is the meaning of the inverse of a matrix. A matrix causes the space to be transformed into something else, and the inverse of that matrix restores that something else to the original space. And that is the significance of an inverse. So if we can invert the matrix that we are multiplying it with, there is always an one-to-one relationship between the original vectors and the transform vectors, because we can go back and forth between these two vectors by simply multiplying it with either the matrix or the inverse of the matrix. But we know that all matrices are not invertible. So what happens then? Well, let's see this example. We have a bunch of vectors here. Let me introduce a matrix. If I multiply this matrix with all of these points, all these vectors are going to lie on the same point. So all these vectors are being transformed into one single point, and that point in this example is a point 6, 0. When that happens, there is no going back, because when you are in 6, 0, there is no way to say from where you ended up here. You could have come from here, you could have come from here, or here, or here. So the one-to-one relationship that existed between the original matrix and the transform matrix does not exist anymore, and hence this matrix does not have any inverse. In fact, if we multiply this matrix with each and every two-dimensional vector of this plane, the whole plane is going to collapse into a single line. Although no one ever tells us what having a matrix and the inverse of a matrix actually means, this is the meaning, this is the geometric significance of not having an inverse, because there is no way to go back where you came from. So as you can see here, a two-dimensional vector space has been transformed into one dimension. And that's not all. When I'm not using a square matrix, the transformation can cause a loss in dimension as well. Let's see an example. In here, we are multiplying a three-dimensional vector with a 2 into 3-dimensional matrix. As a result, our output is a two-dimensional vector. So, the transformation here is from R3 to R2. The transformation has squished a three-dimensional space into a two-dimensional plane. Pretty fascinating, right? Okay, so we are going to stop here for today, and in our next lecture, we are going to try to answer more questions about matrix transformation and how they work. Until then, thank you and take care of yourself.